In our previous video, we very briefly discussed discrete probability distributions, and if you remember, they were the binomial, hypergeometric, and the Poisson probability distributions. We'll continue our discussion of probability distributions by examining continuous probability distributions. And if you remember, that usually results from measuring something. For example, the weight of a person, the distance from a patient parking spaces to the hospital entrance. For continuous distribution, we may want to know the percent of observations that occur in a certain range. For example, the percent of patient parking spaces that are within 250 paces from the hospital entrance. A continuous random variable has an infinite number of variables or values within a particular range. So when you're thinking of the variable, you want to think of the probability a variable will have a value within a specified range rather than the probability for a specific value. And as a refresher, in case you haven't watched these videos back to back, let's get a look at the different types of distributions that we have. And if you're looking for the objectives, as we did with the last session, please look on the video prior to this one, in other words, the video for chapter 6. And we have here our discrete probability distributions, which we briefly mentioned, and our continuous probability distributions, which is what we're going to focus on today. And the one we're going to focus on today in particular is the continuous normal probability distribution. And let's take a look at the discrete and continuous random probability distributions side by side. So when we have a discrete probability distribution, we can put it into a table because we have specific values. For continuous probability distribution, remember there's an infinite number of values that we could have within this specified range. So we depict it with a curve similar to the bell-shaped curve. And it could be slightly different. We're going to talk about the normal curve, which is shaped like the bell curve, but it could also be shaped where one end is stretched out a little bit longer than the other, but we'll get into that in the future. So when we talked about the probability or the distribution in our previous session in chapters 1 through 4, what we were talking about there was counts. How frequently, for example, we have here the mu of 25, and if you remember, that's the population mean of 25. That would be how many times did we count a mean or that value of 25, and let's say these are full increments, so this would be a 24. So how many times did we count 24? And that's how we would do the distribution. Here we're looking at the probabilities, not the actual counts in there. So we would have probability values under this curve that we have here. And as I said, we're going to focus on the normal probability distribution. So how do we go about calculating the normal probability distribution? Well, of course there's a formula for that. And you'll have to memorize this for the exam. No, I'm just kidding. First of all, we don't have an exam. And second of all, I'm not going to ask you to memorize this probability distribution formula because we fortunately don't have to hand calculate this formula. We have, with the age of technology that we have today, we can use Excel and other statistical programs to calculate this out. But even if we didn't have that, we have tables in the back of our book, or in any statistics textbook, just about any basic statistics textbook, you'll find tables of the normal probability distribution. And they won't give you the specific values. Obviously, if we have an infinite number of values, we would have to have an infinitely large textbook in order to have all of the values that are under this curve. But what the book will provide for us are increments within that probability distribution, and we can get a fair assessment if we just have the book and we don't have a calculator that has statistical functions, or if we don't have Excel or some other statistical package, we can always use our book. But if you're interested, you could actually calculate out the particular value. So if we wanted to know the probability that a normally distributed random variable is between infinity and x, we would just plug x into the above equation and it would tell us. Well, actually, assuming you calculated everything correctly, it would tell us. And note that since mu and sigma will change for each of these possible distributions, now you remember mu and sigma will change for each possible distribution. There are an infinite number of these values. Or we could just stick this into a cell in Excel and calculate out our values for us. And if you remember, when we're using the Greek characters, that's because we're talking about the population standard deviation or the population mean, or pi in this case is our standard or the constant pi, 3.14159265, and so on. Well, let's get away from this scary formula and look at some of the major characteristics of the normal probability distribution. In our normal distribution, that's the bell curve that you've probably seen before in that it is symmetrical. Each half is identical and a mirror image of the other half. It has only one single peak on there because it's, remember, there are multimodal or bimodal distributions. This one only has one mode. The mean, the median, and the mode are the same. They are all in the center point of it. And it falls off smoothly from the central value in both directions, and it is asymptotic. That means the curve gets closer and closer and closer to the horizontal line or to the x-axis, but never actually touches that. And again, we talked about this in our previous sessions, where sometimes you'll see the pictures that we get in our depictions where the lines actually touch the x-axis. In reality, we have to recognize that the tails do not actually touch the x-axis. That's more a limitation of the graphics production than it is a limitation of the normal distribution. An important point to remember is that the area under the entire curve, which means all the way out into infinity to the negative side and to the positive side, all the way out on both directions on into infinity, the total area under the curve equals 1.0. Half the area under the normal curve is to the right of the center point over here, and half is to the left of it. So that means that half of the probabilities are on the left side, half of them are on the right side. And the dispersion of this normal distribution is determined by the standard deviation. Now let's take a look at the normal curve or the normal distribution as it's compared to another distribution. Okay, here are the characteristics again. I'm hoping this will at least keep you awake. So the characteristics of the normal distribution are here. This is your reference page. We covered these, and the mean, the median, mode are all equal. So when it's symmetrical about the mean, we could say it's symmetrical about the median or the mode as well, because it is, and they are all in the same place. They are all equal. And let's take a look at some different normal probability distributions. So there's a family of distributions here, and what we see in the top left is that we have equal means, unequal standard deviation. So our standard deviation at the highest peak is 3.1 years, and at 5 years it's our widest, and that's our blue line, and you can see how that affects the normal distribution. Now on the bottom we see that we have the exact same standard deviation, so all of our distributions look identical, but they are all on different means. And in the top right we have unequal means and unequal standard deviations, so we're all over the place with this. And this is just a depiction so that you get the idea of the differences in the distributions that you could potentially see. And it's also to point out that the number of normal distributions is unlimited, each one having a different mean, standard deviation, or both. Now, I hope you can see that between here, here, and here, or among, I suppose we should say among here, here, and here. While we can provide probability tables for discrete distributions, such as the binomial and the hypergeometric, providing tables for an infinite number of normal distributions is impossible. Fortunately, what we can use is a particular normal probability distribution, the standard normal probability distribution, to determine the probabilities for all normal probability distributions. And the standard normal distribution is unique because it has a mean of 0 and a standard deviation of 1. Any normal probability distribution can be converted into a standard normal probability distribution by subtracting the mean from a particular observation and dividing this difference by the standard deviation. So any of these different distributions that we have in this example can be converted to a standard normal probability distribution. So what do you see there? If we can convert any of these to a standard normal distribution and use that as our basis, we can then compare each of these distributions against each other. So again, our formula is to take an observation, a particular observation, and subtracting the mean from this observation and dividing it by the standard deviation. So we have z equals x minus mu divided by the standard deviation, or sigma. And the results are called z-values or z-scores or z-distributions. And it's the signed distance between a selected value designated x and the population mean. So that's our difference right up in here, the distance between a selected value and which is just designated the x, and the population mean mu divided by the population standard deviation. So if we were to take an observation, say here, and then subtract from it the mu, so we would get this distance in here from our point that we've chosen, our x value, minus the mu. Maybe it would be easier if we started over here. We had an x value over here, and we could actually even take this one right here, which is 2107, because that's still on the blue distribution right at the end there, 2107 minus 2000, so our distance is 107, and then we would divide that by the standard deviation of 2000 psi, which I'm not going to do in my head. But that's how we could come up with a z-score. Well, once we did that, if we wanted to, we could do that for each of these other distributions so that we could compare them. So another way to look at this is that a z-value or a z-score is the distance from the mean measured in units of the standard deviation. And you can look on page 229 of your text to find out more about this. But let's go ahead and run through an example where we actually do the whole calculation. So we're going to find the z-score, and we're interested in the time required for a given surgical procedure. Previous data suggests normally distributed times with a mean time of 180 minutes and standard deviation of 20 minutes. And one operation yesterday took 220 minutes. What's the z-value for this operation, or the z-score for this operation? Well, we just plug in the values, and we say previous data suggests normally distributed times with mean time of 180 minutes. So we plug in 180 minutes, that's our mu, our mean time, and a standard deviation of 20 minutes, so that's our denominator. And then we took our one observation of 220 minutes. So that's our x value. So we put in the 220 minus 180, and what do we get? 40 divided by 20. So 220 minus 180 is a 40 divided by 20 equals 2. So our z-score is 220. What if we took the operation that, or we had the value of an operation that took 140 minutes? Why don't you go ahead and pause the video for a second and see if you can calculate that out yourself. Did you figure it out yourself? Well, all we have to do is switch the value out of our x value. So we would put 140 in instead of the 220. We would get 140 minus 180. 140 minus 180 is negative 40 divided by 20. So our z-score would be negative 2.0. So it's the same magnitude, just in the negative as opposed to the positive for this value, or this operation that we had in our first example. And since the standard normal distribution is a nice symmetrical distribution, we can use what's known as the empirical rule to help us determine what proportion of the area under the curve falls within certain standard deviation values. And that should ring true, the empirical or normal rule we talked about previously. So about 68% of the area under the curve is within one standard deviation of the mean, plus and minus one standard deviation. And about 95% is within plus and minus two standard deviations. And about 99.7, almost all of the observations are within the plus and minus 3 standard deviations. And our book has a nice table in the appendix to help us determine the area that's under the normal curve. So this is an area that we see on page 764, and we assume that our pharmacy has the following daily morphine prescription distribution: the mu of 283 grams and a standard deviation of 1.6 grams. What's the probability or area under the curve between the mean and 285.4 grams? So using our z formula from before, which is x minus mu divided by sigma, to get our z-score, we can fill in our values. And we stick in our x, our observation of 285.4, minus our mu, which we have as 283 grams, and we divide that by 1.6, and we come out with 1.5. We can go into our appendix in the back of the book, and you open your books to page 764, go down the column of the table headed by the letter Z to 1.5, right here. Then move horizontally to the right and read the probability under the column headed 0. Why 0? Because we have exactly a 1.5 as our z-score. If we had a 1.51, we would go over here. 1.52 over here, 1.53, and so on down the line. And this, if we find this value, we see is 0.4332. This is the probability that a randomly selected day's morphine prescription distribution will have a mass between 283 and 285.4 grams. Now I encourage you to take out your book and run through this exercise, or at least run through into where you can see how the values line up, so that this image here lines up with what you have on your book, because it's not shaded like this in your book, and it's good to know how to use your particular book, because unfortunately each statistical textbook does it a little bit differently, or many of them do it differently, so it's a little bit difficult to try to keep. You have to go in and learn how to use each book that you get. Now the other advantage is that we can also use Excel and Megastat to help us determine the area under a normal curve. And using Megastat, we can go to Megastat, probability, continuous probability distributions, and normal distribution. And we have the options for calculating P given Z, so we know the Z values and we want the probability, or we can go with the Z given P. In other words, we know the probability and we want the Z values. So there's good information there for us. Now there is a distinction though. Our megastat gives us cumulative probabilities, while the appendix B1 gives probabilities from the mean. Well, what does that mean? Well, let's take a look at that. Excel and megastat can be used to help us determine the area under the normal curve, but we have to be aware of the differences noted in the last bullet. So the appendix in our book gives us the area as it relates to the mean. So it gives us the area under the curve as it relates to the mean. Depending on how we ask our question or the information we're looking for, we may have to keep in mind that we'll have to add the 0.50 into whatever the value is that we get on the positive side of the curve. The next few pages provide a reference for using Excel to calculate the area under the normal curve that may be of help to you. And I'll run through it briefly, but it's here for reference, and you have more information on page 239 of your textbook. So we have a tire company that wants to set a minimum mileage guarantee on its new MX100 tire. It reveals that the mean mileage is 67,900 miles with a standard deviation of 2,050 miles, and that the distribution follows the normal probability distribution. Leighton wants to set the minimum guaranteed mileage so no more than 4% of the tires will have to be replaced. So what minimum guaranteed mileage should Leighton announce? Well, we solve it using the Z formula first of all, and we're using the 4% information. The area is between 67,900, which is our mu, and 0.46, found by the 0.5, because remember, everything to the left is 0.5 minus the 4%. So we're taking the 0.5 over here, and we're saying that if it doesn't get to the 67,900, which really that's the mean, but if it doesn't get to this point of mileage, in other words, has fewer miles than this, we're going to have to replace it. But we don't know what this mileage point is. That's what we're trying to figure out. And what we're trying to find out is this shaded area. If we look at our appendix B1, the area closest to 0.460 is 0.4599, which is good enough for this example. And that gives us a Z value, or a ZALU is the way it's written here. Let's see if we can fix that. A Z-value of negative 1.75. So then we put that negative 1.75 into our equation, and we solve for x using algebra. We move everything around, so we take 2050 and multiply that by both sides, and we get this. And then we subtract off the negative 67,900 from both sides, so we get x equals 67,900 minus 1.75 times 2050, or x equals 64,312 miles that we're looking for. And if we were to do this in Excel, we would use the norm inverse function. Probability would be 0.04. Remember, that's what we're looking for, the 4%. And the mean, we know the population mean is 67,900 miles, mu. And the standard deviation was 2,050 miles, which again goes back to our original scenario. And here's the answer we can see as the preview of what we'll get when we actually put this into a cell. And that's it for today's video, or for this video. You may have more than today's video, more than one video in today's set of videos.